Hello everyone, I welcome you to the course Unmanned Air Vehicle Design. Today we'll discuss about Fuselage Aerodynamics. Fuselage Aerodynamics. The fuselage significantly impacts a UAV's aerodynamics. Its design is crucial for optimizing the aircraft performance by influencing both drag and lift. The fuselage design process for a UAV is a complex and iterative procedure that begins with identifying the mission requirements and internal components, ultimately shaping the aircraft's aerodynamic and structural characteristics. Initial design steps and influences. The design process begins after the payload and design requirements are identified. The very first step is to decide about the fuselage configuration and determine the internal arrangement. This initial decision is crucial as it significantly influences all subsequent fuselage parameters. Fuselage configuration design is considered a conceptual design at the fuselage level and relies heavily on accumulated experience rather than detailed calculation at this preliminary stage. The fuselage configuration is a function of the internal arrangement, meaning that to specify the location for each internal item, one must first identify what component needs to be accommodated. Internal arrangements and components. The volume and external shape of the fuselage are direct functions of what is intended to be stored inside. A conventional unmanned air vehicle fuselage typically comprises several sections, each with unique design requirements through their relative locations are determined early in the design phase. A conventional unmanned air vehicle fuselage typically comprises several sections, each with unique design requirements, though their relative locations are determined early in the design phase. First one, autopilot station. What kind of autopilot system is needed for unmanned air vehicle design? Based upon the configuration, this autopilot system is being housed inside the fuselage. Then load compartment, what all the payloads it will be carrying. According to that, the cross section will be designed. Next, nose section, rear section, fuel tanks, communication system, radar, internal systems for electrical, mechanical and hydraulic, engines if it is housed by the fuselage. Rules for internal arrangement. There are 7 basic rules guiding the internal arrangement and placement of allocated items within the fuselage. First and foremost, keep the fuselage as small and compact as possible. The arrangement should be as symmetric as possible from a top view perspective. There must be sufficient space to accommodate all equipments and devices. Usable loads such as fuel must be close to the aircraft's center of gravity. The satellite radar dish must be allocated in an upper or lower place to ensure a clear line of sight with communication satellites and ground stations, enabling uninterrupted communication. The arrangement must ensure that the aircraft's center of gravity is close to the wing fuselage aerodynamic center. If necessary, any piece of equipment can be placed or installed outside the fuselage. For example, a camera for photography and video is often the best placed underneath the nose for 360-degree access to the targeted area. This is the internal arrangement of HALE unmanned air vehicle and high speed combat unmanned air vehicle. So, in low speed, high altitude, long endurance civil unmanned air vehicle, we have a camera base here. This is the nose gearbox, the front nose. This is the wing box. This is main landing gear bay where it is stored. When the engine is installed inside the fuselage, it will be here at the back side, rear side of the fuselage, propeller engine. This is communication system. This is autopilot system. This is the fuel tank through which fuel will be supplied through a pipe system to the engine. These are the systems, and this is the antenna, the radar dish. And for high speed combat unmanned air vehicle system, we have a seeker dish here. This is the landing gear bay. This is the wing box. This is main landing gear bay, which is inside the wing box. We have fuel tanks, autopilot system, communication system, equipments, and this is turbofan engine, which will be driving this high speed combat unmanned air vehicle, and fuel will be supplied from this tank to here. Determining fuselage parameters and shape. The two major fuselage parameters determined during the design process are fuselage length and maximum diameter. These, along with the overall configurations, are functions of various design requirements. Three important components significantly contribute to the fuselage shape. Largest component, this naturally determines the maximum diameter of the fuselage. Engine, if housed by the fuselage, the engine is a major determinant of shape. Radar dish, the radar dish influences the curvature of the adjacent fuselage portion to ensure perfect communication efficiency. Aerodynamic considerations. Aerodynamic design is fundamental to the fuselage with a focus on achieving specific goals like low drag. The fuselage is a substantial contributor to the aircraft drag, 30 to 50% of zero lift drag. So, minimizing it is a primary expectation. To achieve low drag, the fuselage designers aims for an airfoil-like section from the side view, often by adding a semicircle to the nose and a cone to the rear, cone or a semicone. The top view is recommended to follow a symmetrical aerofoil to avoid yawing moment. The fuselage also encloses components like landing gear, engines, fuel systems to reduce overall aircraft drag. Lift generation. The fuselage is expected to make a positive contribution to the lift, while it typically produces about 5% of the total lift. In a basic configuration, it can be aerodynamically designed to provide as much as 20% of the total lift. Blended wing fuselage designs, for example, X45 and X47, are ultimate solutions for maximizing lift generation, where the entire aircraft contributes to lift, reducing weight, wetted area, and drag. Symmetry. External symmetry is recommended, particularly about the exit plane, to ensure a zero rolling moment. This means the fuselage must be symmetric from a top view. The aerodynamic characteristics are fundamentally related to the fuselage cross section and nose shape. The final solution involves trade-off studies to yield the optimum design. Structural and internal system integration. Fuel tanks. Fuel tanks can be accommodated by the fuselage, requiring calculation of the necessary volume based on fuel mass derived from mission range and endurance using Braggett's equation, and fuel density. Wing box. For structural integrity, UAV designers often prefer the wing main spar to carry through the fuselage, forming a wing box. This section of the fuselage is allocated volume to accommodate spar and is the strongest structural area, handling the largest bending moments and stresses generated by wing lift. Pressurized compartments. Although unmanned air vehicles generally don't require pressurized cabins due to the absence of human factors, some avionic and payload components may not operate efficiently at low pressure. Therefore, a pressurized compartment is sometimes necessary to house these sensitive heat generating components, as seen in the Global Hawk's aluminum fuselage. It is particularly important for convection and conduction cooling techniques. Structural shape. From a structural standpoint, the most efficient, strongest shape for a slender pressurized fuselage is a cylinder with hemispherical end caps, maintaining symmetry with respect to exit plane. Redesign for new payloads. If an existing unmanned air vehicle needs to accommodate a new, larger payload, the fuselage must be redesigned and elongated. An example is the Avenger ER, which underwent a modified fuselage design extended by 4 feet to house larger payloads and more fuel. Aerodynamic considerations are paramount in the design of unmanned air vehicle fuselage, significantly influencing its configuration, external shape, and overall flight characteristics. Relationship with fuselage design. The aerodynamic design of a fuselage is a direct function of its configuration and internal arrangement. The fuselage volume and external shape are determined by what is housed inside. Objectives for external shape. The external shape of the fuselage is driven by several aerodynamic objectives, including low drag. Minimizing drag is a critical goal. The fuselage typically contributes a significant portion, 30 to 50%, of the aircraft's zero lift drag. To achieve low drag, the fuselage designer should select a cross section that resembles an airfoil shape. Second one, low pitching moment. Third one, zero rolling moment. This is crucial and necessitates a symmetric fuselage above the exit plane. From a top view, the fuselage must appear symmetric. If we see, this is considered to be the fuselage, and if we draw a line which is bisecting this fuselage from the center of this to center of this, this should be symmetric. This area should be equal to this area. Low yawing moment. To avoid any yawing moment by the fuselage, its top view is recommended to follow a symmetrical airfoil. Lift generation. The fuselage may also be designed to generate as much as lift as possible. While in a basic configuration, it might only produce about 5% of the total aircraft lift, it can be aerodynamically designed to contribute up to 20% of the total lift. The ultimate solution for the significant lift generation is a blended wing. Blended wing fuselage design, for example, X45 and X47, where the wing is smoothly blended into the fuselage, allowing the entire craft to generate lift and reducing weight, wetted area and drag. This is an example of X45A UCAV by NASA Dryden Flight Research Center. This is having blended wing configuration. This fuselage and this wing are blended to each other. Streamlining. From a side view, streamlining must be considered, which often involves adding a semicircle to the nose and applying a cone or semi-cone to the rear fuselage. Component enclosure for drag reduction. To reduce overall aircraft drag, the fuselage is highly likely to enclose other major components and systems such as landing gear, the engine, the fuel system and the power transmission system. CG placement. An important internal arrangement rule for aerodynamic balance is that the aircraft CG must be close to the wing fuselage aerodynamic center. Relationship with cross section and nose shape. The aerodynamic characteristics of the aircraft have a fundamental relationship with the cross section of the fuselage and the shape of the nose. Conclusion for this lecture. Fuselage design plays a critical role in unmanned air vehicle aerodynamic performance, directly affecting both drag and lift characteristics. The design process is iterative and begins with mission and payload requirements, which shape the internal structure and aerodynamic features of the fuselage. Early decisions on configuration and internal layout are vital as they influence all future design parameters and overall aircraft efficiency. These are the references used for the lecture. Thank you. We'll meet in the next lecture.